En realidad está aquí. A ver.
Pero puedes ir en el menú arriba a View, ¿puede ser? A ver. No.
Okay, so I think we are online now.
Okay.
Yeah. So Alberto, everything is ready, or you need
1 second, please.
Yeah. Don't worry.
To set the full screen, but I cannot do it. Okay, I think it's working now.
Yeah, I see your screen. Yes.
Can you see it, the full screen?
Yeah, it seems so. Yeah.
Okay, great.
Okay. So welcome back, everyone. So we continue the morning session with the second lecture from Alberto, talking about extragalactic background light. Please, Alberto.
Okay, thanks. Hello, everybody. So we are going to switch gears and we are going to go from the dark to the bright side of the universe. We are going to try to talk about how much light there is in the universe. And this seems to be something ambitious because I have only 45 minutes, but I hope you get some glimpse of the topic. You learn why this can be important for some strategies of looking for dark matter. So the problem of measuring how much light there is in the universe is coming from an ancient question, but it was put written in a more formal way by the German astronomer Heinrich Olbert. It was a few hundred years ago. And at that time, of course, the standard cosmological framework was different. And this is known as the Olbert paradox. And the Olbert paradox says the following. So in an infinitely old universe that is covered by an infinite distribution of stars, the night sky should be bright in opposition to what we observe. Of course, the solution to this problem is given by the current cosmological framework. This is seen simply in this animation, how given enough time, you will find a line of sight in this type of older universe, a point of light from everywhere in the sky. So this is just, this animation is very simple. It's just taken from the Wikipedia only to illustrate the effect. So I don't think I need to tell you that the current cosmological framework is lambda CDM. You already saw this at the beginning of the school, but let me remind you in the galaxy evolution context that galaxies, we are already seeing galaxies at early times, as early as a few hundred mega years after the Big Bang. We have already detected these galaxies. So galaxy evolution started pretty early in the age of the universe, and it is, of course, going on till our days. One of the consequences of galaxy formation and evolution is the emission of radiation that is typically produced within galaxies and eventually escape to the intergalactic medium, accumulating in this intergalactic medium. These photons are not only accumulated, but are also redshifted by the expansion of the universe. So the accumulation and redshifting of all this light produced in galaxies form what we know as the cosmic diffuse backgrounds. One special case is the CDM, and I will quickly show you about it in the next slide. So This is the spectral energy distribution of these cosmic diffuse backgrounds. So we see that they essentially cover the whole electromagnetic spectrum, going from gamma rays all the way to radio. You can see here, I'm not totally sure if you see the pointer, but you see here the CMB that follows the shape of a Black-Body spectrum. We see the gamma ray background, X-ray background, and today we will focus in this region that covers the optical plus the infrared. Okay, so in this kind of representation, it is also important to note that the area inside the curve, inside this data, is a representation of the energy in the background. So you can see clearly that the CMB is the most energetically speaking, the most energetic background, followed by the EBL. That is this combination, as I said, of the optical and infrared. The optical peak is produced basically from starlight with a little contribution from AGNs, and the infrared part of the EBL is produced by the absorption and re-emission of stellar light by dust towards these higher wavelengths. So how do we measure the EBL? Actually, this is a very challenging task. You can think that we want to measure this isotropic diffuse faint signal when we are in a point in the universe from Earth where everything essentially around us is emitting to the wavelength that we are interested in measuring. So the most or the first serious attempt of measuring the EBL was probably done by the COBE satellite. COBE had an instrument named DIRBY that has a field of view of about 0.7 square degrees. This is about the size of the full moon. And what DIRBY did was to scan the whole sky in these photometric bands, trying to map the whole sky. I'm giving you here 3 examples in these 3 different bands from 125 microns to 3.5 microns. DIRBY actually got to measure as far as 240 microns. And you can see in these examples, of course, this is galactic coordinates. So what you are seeing here crossing the map is the brightness of our own galaxy. So the main problem to measure the EBL is actually zodiacal light. This is light that is scattered from interplanetary dust coming from the sun. Zodiacal light is really bright. You can even see it by the naked eye, just under the right conditions. And to give you some feeling of the numbers that we are talking about here, I'm showing you this table where you see the total intensity average measured by DIRBY. You see here it is 140 in these units. And you see that zodiacal light is about 100. So after subtracting all the contributions that are contaminating your measurement of the EBL, what you get is this faint signal that we call the EBL, that is much fainter than the total signal that you are getting. You need to remove the contribution from zodiacal light, the interstellar medium, and the bright of localized stars in our galaxy, both faint and also bright. So the note here is that the EBL is an order of magnitude lower than the foregrounds, and of course it is subject to very large systematic uncertainties. Even in this difficult technical situation, we have some more or less robust measurements of the EBL. This is a plot showing you spectral intensity versus wavelength. You see here on the left the optical peak, and you see on the right-hand side the peak from dust re-emission. Okay, you see that the scatter of the data coming from different instruments is actually significant. So there is also an alternative and complementary approach of measuring the EVL that is not, so the previous one is known as absolute photometry or also direct detection, but we now have this galaxy count technique. So this technique is based on measuring using deep galaxy surveys that detect a small or observe small regions of the sky. So you try to go as deep as possible in your surveys. So you try to be as complete as possible in the observation of galaxies in your in the field that you are working with. So essentially, you want to make plots of this type where you have galaxies per square degree and per magnitude in the y-axis, and you write the magnitude of the different galaxies in the x-axis. So you build this type of plot where every one of these more or less lines you see here, these are different photometric bands. Okay, so in summary, when you integrate the area inside one of these curves for a given photometry, what you are getting is how bright is the sky in that band from your survey. Okay, so this is a very robust way of estimating the background that you are seeing exclusively due to the galaxies that are making it into your survey. So this is one of the downsides of these techniques, because you may be losing light from galaxies that are too faint, either because they are intrinsically faint or because they are too far away. So another problem of this technique is cosmic variance, because the universe is homogeneous and isotropic at large scales, but it doesn't happen in small scales. So it is possible that the small field that you are surveying is for some reason a bit special. So it is a bit dangerous to make the interpretation from a small field to the whole universe. Anyway, now in this plot, I'm also adding the data from many deep surveys. All these field symbols are different data in different photometry from different surveys in general. And you can see that they tend to agree with the lower bound of the direct detection data, right? At least here in the optical peak. Okay, so moving on, we saw that we can measure the EVL using absolute photometry, also using galaxy count, and we can also use a third approach that is also based on galaxy survey data, and it is building empirical models of the EVL using either theoretical or observational models. There is actually a whole business, many different strategies for building these models. Some of them are more theoretically based, some of them are more observationally based, some of them are based only on local data that is extrapolated towards higher redshifts, and others, probably the most sophisticated ones and most modern, they are based on data that is taken over as many redshifts as possible, going as deep as possible. So in this plot now, I'm showing you the direct detection data here in gray, and also showing you the galaxy count data here in these red symbols. And now I'm adding up the results from many different strategies for modeling the EVL. In summary, I would say that most of the models converge to the galaxy count data, and in fact also to the lower cloud of the direct detection data. I think most of the people working on EVL now believes that this very high intensity data is actually contaminated by zodiacal light that has not been subtracted in in a correct way, essentially, or some foreground that is not totally understood. So in essence, all this, the current picture that we have, this is in the local universe, is that this lower direct detection cloud of data agrees with the galaxy count data and also with most of the ABL models, at least in the optical peak. The situation is a bit different here in the far infrared peak, and also the situation is very different at high redshift, because if you look at the results from different models at redshift already of 2, you can see that the intensities that the different models are estimating strongly diverge, essentially at all wavelengths, and even at, you can see that at redshift 3, the discrepancies between models is actually huge. So we need to make a better work in the modeling of the ABL in the far IR, and also on the evolution of the ABL, and that's something that we are trying to solve in this Saldaña and Lopez paper. So, but I'm not going to tell you more about that today. I'm going to go to the fourth methodology of estimating the ABL, and this is actually the reason why this is important for some strategies of searching for dark matter. So the process here is that you have very high energy photons. These are photons with energies above, let's say, 30 GeVs that are coming from extragalactic sources. Let's say a gamma ray burst or a blazar. So you have these very high energy photons crossing cosmological distances, and there is some probability that these very high energy photons interact by pair production with the lower energy photons of the ABL. Okay, you probably are aware of the annihilation process. It is a better known, I think, interaction. So the pair production is the reverse process. So you have 2 photons that create a positron and an electron. Okay, so the net effect of this interaction is that the fluxes, the gamma ray fluxes that we are detecting with our telescopes, both from space, let's say from Fermi, and from the ground, from the using the IACTs, I will tell you a bit more in the next slides. These fluxes detected by our telescopes are strongly attenuated by the EBL interaction. So the fluxes that we observe, this equation gives you analytically what I mean. So the observed fluxes are exponentially attenuated by this tau, that is a parametrization of the EBL attenuation that is dependent on both the energy of the gamma ray photon and on the distance to the source that is emitting those gamma ray photons. So this is what we know as the intrinsic spectrum, and the intrinsic spectrum is that one that we would observe if there were no EBL. You need to be careful. This is not the emitted spectrum from the source, because there is a difference of redshift. Okay, so this would be redshifted relative to the one that is coming out directly from the reference of the source. So analytically, this tau, this optical depth that describes the EBL interaction, is given by this long equation, but don't get afraid. It is actually very simple. It is like any interaction where you have 3 different terms. You have a term of the distance that is crossed by the light. Then you have another term that gives you, it is depending on the cross section of the interaction that is being produced, that attenuation. And you also have another term that is a measure of the density of the medium, that in our case is the EBL photon density. And this is important, the evolution of this EBL photon density, because you need to account for the evolution of the EBL from now till the redshift where the gamma rays were emitted. So in this case, of course, the distance is typically known. It is the distance from the source. Then you have the cross section that in our case is the per-production interaction. Okay. So to give you an idea of how this tau typically looks, this is showing tau versus energy. This is 100 GeVs. This is 1 TeV, and these are, I think, 30 TeVs. So you see that tau is an increasing function with energy and also with the redshift, because these curves are for sources located at different redshifts. What I'm showing here in this lower side plot is the exponential of minus tau. So this is the flux attenuation that goes in this equation. So let me tell you very quick about the instruments that we are using for detecting these gamma rays. This is only for completeness, because I think you guys will learn much more about these instruments next week. So we have Fermi. That Fermi is an all-sky survey. It has a very large field of view, and its peak of sensitivity is about 1 GeV. So Fermi tells us and give us a very good description of the sky at about 1 GeV. Then we have the imaging atmospheric Cherenkov telescopes, that they have a much smaller field of view, but they have much higher sensitivity at the energies of about hundreds of GeVs and about also one TeV. So the most common examples and the most active telescopes are Veritas in Arizona, HES in Namibia in the southern hemisphere, and we also have MAGIC at La Palma. As you probably know, CTA is being now built. It is going to be the next generation of Cherenkov telescopes. It will be built in La Palma, and also another observatory in the southern hemisphere. And the first stage of CTA, the large size telescope, is already built and is working in La Palma. So this is an artistic impression of the southern side of CTA, and this is a real picture of how the LST, this first telescope of CTA, is looking in La Palma. So coming back to Fermi, because I will tell you a bit more on the results that Fermi is providing in EVL attenuation. Very briefly, again, Fermi is actually more similar to a particle detector than to an actual telescope. Thinking about telescope has something built with mirrors, right? So Fermi has a tracking system. It has a calorimeter that measures the photon energy of the incident gamma ray that is converted to an electron and positron pair, and it has also an anti-coincidence detector that helps to reduce the background. So Fermi is actually giving us extraordinary results on the sky. I'm showing you here an old image of the year 2000 of the satellite that we had before Fermi, looking at to the gamma ray sky. This is Egret, and you can see how Egret actually had very little positional accuracy, so it had also not really good sensitivity, but it was very good at the time. But you can clearly see how the huge step that we have accomplished from Egret to the sky that we see now in Fermi. We see thousands of sources all over the sky. We see prominent diffuse emission from our own galaxy here, and we are able to resolve extension in many of these sources. So it really has provided beautiful results and has opened completely a new window to the higher energy sky. So very briefly, let me tell you about the catalogs that Fermi is building. So the main catalog, also known as broadband catalogs, are these known as FGL catalogs. And as you can see, they cover a broader energy range of the essentially where Fermi is the latch detector is sensitive. Although, as I told you, the peak of sensitivity is here at the 1 GeV energy range. So then later we decided to build the FHL catalogs that are focused on the higher energies, and the idea is trying to get a closer representation of the sky that is accessible to the IACTs. Okay, so this is the reason why we moved from 1 FHL to the 2 FHL, where the energies that we were analyzing here were much closer to the 100 GeVs that are accessible to the TeV telescopes. And then we also built the 3 FHL catalog, trying to go a bit lower in the energy threshold to try to be some tool for CTA to plan observations, since CTA will have a lower energy threshold than the current generation of ACTs. And then, not so long ago, the latest release of the catalog was made published. That it is the 4FGL, and now we have the data release 2 of 4FGL that is built with 10 years of telescope times. So you can note how Fermi has detected thousands of sources with a very good characterization of the flux and index of the sources, and also positional properties. So I'm going to tell you now one of the strategies that we use to use EVL attenuation to measure some properties of the EVL and some properties of the universe. For this, we are using as a tool the source that are blazars. It is actually the dominant source in number in the Fermi catalogs. And blazars are supermassive black holes at the center of galaxies. These black holes are active, and they have jets that are detected in radio and also in gamma. These are radio loud sources that just by chance turns out that these jets are pointing toward Earth. So the typical broadband spectral energy distribution of these sources is like this. It has a double peak. This lower energy peak is typically produced by synchrotron emission, and this higher energy peak is the one that we detect both with Fermi and also with the TeV telescopes. Okay, and this second peak, this higher energy peak, usually is produced by inverse Compton, or also it can be produced in some cases by hadronic scenarios, but I'm not going to go into this here. So let me tell you how we measure this optical depth using Fermi. So we used a catalog of 9 years of lab data, where we have 739 blazars plus 1 GRB, all of them with redshift, because we don't have redshift for all the blazars that Fermi detects. You can see here the distribution of blazars that is in our sample. But what is important here is to tell you about this strategy. Okay, so what we use is the broadband energy range that is covered by Fermi, that goes from energies where the EVL is not affecting, the EVL is not producing attenuation in the fluxes, but at these lower energies, but it is indeed attenuating the higher energies that also Fermi is being sensitive to. So very broadly, this technique, what we do is to somehow extrapolate the spectrum from the lower energies, that is unattenuated, towards the higher energies, that it is unattenuated, to somehow figure out the intrinsic spectrum at these higher energies, where we can compare with the observations to derive properties of tau. Okay, so essentially you compare the observed spectrum with the intrinsic spectrum that is coming from these extrapolations, and then you are able to get the measurement of tau. Okay, so this technique is not new. It was pioneered by the Fermi-Lab collaboration in the year 2012, but at that time we didn't have so good data, so we were able only to detect this EVL attenuation in some broad redshift range here in the local universe. This is from redshift 0.2 to 0.5, and then we have a very wide redshift range where we also could detect somehow significantly this EVL attenuation. However, now we have way more data. We are able to go from this detection that we did in 2012 to this characterization of the optical depth and over a significant range of energy, and also over 12 redshift beams, going all the way from the local universe up to redshift of 3. So this was actually a huge step forward in the measurement of the optical depth from the EVL using LAT data. So I told you about this because I wanted to introduce this concept that it is very important, and it is the cosmic gamma ray horizon. So the cosmic gamma ray horizon, you can see it easily in this plot. If you plot here the maximum energy of the blazars detected by Fermi as a function of redshift, you can see how this type of plot is divided into two different regions. You have this region where you have data. This is the maximum energy from the different blazars, but you see that you don't have any blazar at these high redshifts emitting at these very high energies. The reason is that these very high energy photons coming from very far away are being attenuated strongly from the ABL. So that's why you don't have any photon in this region. So the difference between these two regions is what we know as the cosmic gamma ray horizon. And you can derive it from here because by definition, it is the energies at which the optical depth becomes the unity for different redshifts. So from the measurement of tau in these 12 redshift beams, you are able to say, okay, so the tau is 1 at this given energy. Okay, so then you can plot 1 point here in this type of plot. Okay, so you repeat the same exercise for the 12 redshift beams, and you are able to make this wonderful characterization of the cosmic gamma ray horizon over a very significant time of the universe up to redshift of 3. Okay, so all this is coming from the detection of gamma ray blazars, and you can now also overplot some of the predictions or some of the estimates from the different EVL models, and you can see how the models were actually doing pretty well in the derivation of the cosmic gamma ray horizon. So let me check the time. Okay, so I'm running out of time. So very quickly, I will tell you a bit about this strategy that we are using for measuring the Hubble constant using gamma ray attenuation. I think it can be interesting for some of you. You probably have heard or will heard about this tension that is happening now in the measurement of the Hubble constant from different strategies. So it seems that some strategies are pointing towards a much lower measurement, a much lower value of H0 than other techniques. So some people claim that there is an almost 5 sigma discrepancy between these measurements. So you can also use the EVL and gamma ray observations to try to say something about this problem. So essentially, you have here the cosmology that is coming in two terms in this equation of the optical depth. One here in the distance, you need to assume a cosmology, and another one here in the EVL photon density evolution. Depending on the cosmology, the EVL photon density evolution will go in one way or another. So we can use this since we already measured all the optical depth using the Fermi data, as I showed you before. We can now fix an EVL model here, and what we do is to leave free the optical, the H naught in the parametrization of the distance and on the parametrization of the EVL photon density evolution. We can build a likelihood where tell us what H naught is better compatible with the independent taus that we are measuring from blazars using the LAT. Okay, so this is the result for two different EVL models. We have for this model in purple and this other model in orange, and the combination of the results from the two models is what we are calling this work EVL combined. This way we have some estimate of the systematic uncertainty that we are introducing in the measurement of H naught by assuming a given EVL model. Okay, so you can see that the value that we are getting using our new methodology is supporting the lower values of this discrepancy between the two different sets of methodologies. Okay, so yes, I'm finishing with my take-home messages. So I just want you to realize that there is fundamental information about cosmology and also galaxy evolution that is encoded in the extragalactic background light, and gamma ray observations can be helpful for extracting this information. It is very important for you, for instance, for using using the gamma ray background to derive properties of dark matter. You need to account for this EVL attenuation, because the EVL makes the universe not completely transparent to the propagation of gamma ray photons. This means that gamma ray observations are in general affected by EVL attenuation. And this is the end of my talk.
Thanks a lot, Alberto, for the talk. Is there any questions either on chat, or you can unmute yourself to pose it?
Hi, can you hear me?
Yes, I can hear you.
Okay. Yeah, when you showed the direct measurements of the EBL, there's a gap in the mid-infrared. Could you comment on why we don't have much data on this range?
Sorry, I stopped sharing my screen to check the chat. So let me go to my slides. So can you see my slides?
Yes, yes.
Okay. So here?
Yeah, for instance.
So can you repeat your question, please?
So in this region, I believe it's mid-infrared, there's no much points and there's no much data. So
yes, that's actually a good observation. And the reason is because the zodiacal light is much brighter in the mid-infrared than at other wavelengths. So in the mid-IR, it is even more difficult to make an estimate of the EVL using this direct detection technique.
Okay, thanks.
Yeah, any other question?
Sorry, I have one. Do you hear me?
Yes, I can hear you.
Okay, so it's also about this zodiacal light. So I was interested, maybe if you have some insights, since I know it is quite hard to estimate it, and it puts up a really large uncertainties on the measuring the extragalactic background light. Is there maybe some method which could be used to estimate the, or which would be the best method to estimate the zodiacal light in order to remove those impacts on the measuring of the EBL itself?
Yeah, that's also a very good question. I can tell you that the best way of removing the contribution of zodiacal light would be going outside the zodiacal cloud. So there are missions, and there are some data here already from the Pioneer that was sent to the outskirts of the solar system, and from there you can make a much better measurement of the EBL, because you are going out of this cloud. Essentially, that would be the ideal thing. Would be to go at about Jupiter. You start the zodiacal cloud start to be very faint. So more or less about 5 AU, you get rid of all these foregrounds. So the ideal thing to do would be to send a satellite outside this 5 AU, where the zodiacal cloud is stronger. So that would be an ideal mission to design to measure the EBL.
Okay, thank you. And one maybe other question which connects to this one, since if I'm not wrong, for the satellites and the instruments in the sky, it's much harder to detect diffuse radiation than point sources. So would that also, if we go even outside this zodiacal cloud, would that have probably maybe some impact on the measurements that we would get from such a satellite?
Yeah, definitely. I think so. Yeah.
Okay. And the last question, sorry for too much questions. I wanted to ask about this article of yours, maybe not the last slide, but the one before. Is it the one from 2019, a new measurement of the Hubble constant and matter content of the universe using extragalactic background light gamma ray attenuation?
Yes, that's those are the results that I have told you in the last slides. Yes.
Okay, thank you. I want to read it, so just checking. Thank you.
Yeah, there is also in the chat, Alberto. So this, what about the EBL and dark matter searches from Lorenzo?
Well, there are some ideas that I'm not sure how much. So there are some ideas that in the past some dark matter particles could have interacted in them, producing some signature, some of these relic particles that can produce measurable signature into the ACBL. But that's not something that I have researched myself, but I've heard about some of those ideas.
Great. And then the last one, what are the sources which contribute to the radio part of the EBL? From Aditya.
So the radio is not actually included in the EBL. The EBL gets to at about a few hundred microns. So that would be the far IR. For the radio, it is outside the EBL. The radio background is coming from a different, completely physical origin than the EBL.
Okay.
So if I can comment, just a second on the previous question, Brian, just a second. So maybe just to recall the students why we actually brought this EBL talk to our school. No, I remind you guys that this is all, the EBL is one of the ingredients that you always have to include in your annihilation flux calculations. For instance, when you are dealing with extra-galactic objects, right? So as soon as you go farther from, as soon as you don't work in our own galaxy, but you go farther and consider other targets like galaxy clusters, or you want to compute the extra-galactic annihilation signals as a whole, you really need to include in your calculations the effect of DBL, the one that Alberto just mentioned, right? Like this attenuation of the annihilation of the gamma ray flux, which will be in our case annihilation flux, right? So the EBL is really a very important ingredient, a very critical ingredient for dark matter searches when it comes to star-galactic sky. Okay. And then also, just for free, I would also like to remind you that there's a particular, there's a specific particle, no, that could be also part of the dark matter, which is the action-like particle. We will hear more about this on Tuesday. And in this case, the action-like particle can actually change the predictions that Alberto is telling us, and can really affect the way the EBL will be basically measured by us, right? So there's a full game between the action-like particles and the EBL that many people are exploring, have been exploring for a few years now, and you can always tell a lot about action-like particles by studying the EBL too, right? So that's also something to keep in mind as a connection with the dark matter search. Okay, but again, we will be hearing more about this on Tuesday. Yes, and logarithm violation. That's true, Ivana. Very good. Yeah, good point too. We don't have a talk on that, but yeah. But probably Manuel will talk about that also briefly. Okay, so just the 2 cents.
Okay, so I think we can go to the next session. So thanks a lot, Alberto, again.
Yeah.